Okay, get ready, because we're about to go deep down into the quantum realm.
That's right. It's a place where things aren't always as they appear.
Yeah, definitely not our everyday experience.
Get ready to completely change how you see reality.
Exactly, we're talking about quantum mechanics.
And it all started with a really simple observation.
In this deep dive, we're going to explore the history of quantum mechanics.
We'll unpack how these big discoveries totally changed how we see the universe.
Our source material has some great examples, like, have you ever noticed how the color of something changes when it heats up?
Oh, absolutely.
Like a blacksmith working with metal, it goes from red to orange to almost white hot.
Yeah, and that's a perfect example of something that seems simple, but pointed to a huge gap in what we knew back then.
They must have thought, well, that's weird. Why does it do that?
Right. And it wasn't just blacksmiths. This was a problem for physicists, who called it the ultraviolet catastrophe.
Okay, that sounds a little dramatic. Ultraviolet catastrophe.
Well, it was a big deal.
What is an ultraviolet catastrophe?
Yeah. Basically, the physics of the day predicted that a hot object should just keep emitting energy more and more, especially as it gets hotter.
So every time you heat something up, you're basically creating a mini sun.
It's not quite that bad, but you get the idea. The math just didn't add up. And that's where Max Planck comes in.
They called him a reluctant revolutionary in what we read.
Yeah, in 1900, Planck came up with this wild idea.
Yeah.
What if energy isn't this smooth, continuous thing?
Like water flowing from a tap.
Right, exactly. What if it's more like grains of sand? Each grain is a specific amount of energy, a quantum.
Okay, so instead of a steady stream, it's like these little packets of energy.
You got it.
That's a pretty big shift in thinking.
It was huge. And the best part, it actually explained this ultraviolet catastrophe problem.
Saved the day with a totally new idea.
And this, my friend, is how quantum mechanics was born.
So Planck solved one big mystery, but then what?
Well, then comes, of course, Einstein.
Of course, it's always Einstein.
Always. He took Planck's idea of these quanta and used it to figure out something called the photoelectric effect.
The photoelectric effect.
Mhm.
Sounds familiar, but I need a refresher.
Basically, you shine light on certain materials, and they spit out electrons.
Okay, so light can knock electrons loose. Got it.
Right. But the weird thing was, no one could explain why it happened.
It seems pretty simple.
No, it was anything but. It led to this big debate about whether light was a wave, like ripples on a pond.
Right, or if it was a stream of particles.
Yeah, like tiny little bullets of light.
It's one or the other, right? It can't be both.
And that's where Einstein comes in and blows everyone's minds again.
Let me guess. He says it's both.
Bingo.
Okay, now I'm really lost. How can something be a wave and a particle?
It's a tough one to wrap your head around. But Einstein showed that light can act like it's made up of these tiny packets of energy called photons.
So it's like light can switch between being a wave and a particle.
It's more like it has properties of both all the time,
Yeah.
depending on how you look at it.
Okay, so light is doing its wave-particle thing. But what about atoms themselves? So we left off talking about the structure of the atom.
Right, and up to this point, the model was that electrons orbited the nucleus, kind of like planets around the sun.
Yeah, nice and organized.
Right, that was the model proposed by Niels Bohr in 1913. But it turns out, well, the atom is way more complicated than that.
Let me guess, it's not that simple.
Not even close. Think about it. If electrons are just zipping around, why don't they just spiral into the nucleus?
Good question. Why don't they?
Well, Bohr proposed that electrons can't just exist anywhere in the atom. They have to be at specific energy levels.
Okay, so instead of orbiting smoothly, they're restricted to certain distances from the nucleus.
Exactly. Like rungs on a ladder, they can be on this rung or that rung, but not in between.
And I'm guessing this ties back to those distinct lines you see in an element spectrum.
You got it. Each line in the spectrum represents an electron jumping between those energy levels.
So it's like the atom has its own secret code, and each jump transmits a specific frequency of light?
You could say that. It was a huge clue that something quantum was going on inside the atom.
So Bohr's model, it had some things right then.
It did for the simplest atom, hydrogen. But when you start looking at atoms with more electrons,
It falls apart.
well, let's just say it needed some major work.
So what came next? Our sources mention something called the Stern-Gerlach experiment.
Oh, yes. This one is a classic.
Tell me more.
Picture that you've got these silver atoms,
Uh.
and you fire them through a magnetic field.
Okay, I'm trying to visualize this.
Yeah.
What happens?
Well, according to the physics of the day, those atoms should have just scattered randomly.
Makes sense, like a bunch of tiny magnets all jumbled up.
Right. But that's not what happened at all.
They didn't scatter randomly. What did they do?
They landed in two very distinct groups.
Two groups, like they were being sorted somehow.
Exactly. It was as if those atoms had some property that could only be up or down, nothing in between.
Right. Okay, I'm hooked. What was this mysterious property?
That's what we now call spin.
Spin, like the electron is actually spinning.
Well, that's the image that comes to mind. But it's not quite that simple. It's more accurate to think of it as an intrinsic property of the electron, like a built-in angular momentum.
So it's not really spinning, but it has a property that acts like it is.
You got it. It was another one of those aha moments that showed the quantum world operates by completely different rules.
Okay, so we've got light acting like particles, and now electrons with this spin thing. Is it just me, or are things about to get even weirder?
Oh, you have no idea. Just wait till we get to Louis de Broglie.
What did he do?
He flipped the script completely.
How so?
Remember how light, a wave, could also act like a particle?
Right, the whole wave-particle duality thing?
Well, de Broglie asked, what if matter, the stuff we're made of, also had wave-like properties?
Wait, you're saying everything around us, even ourselves, has a wavelength?
In theory, yes.
Okay, now that is a mind-blowing idea.
It was a radical concept. And to prove it, they actually did an experiment with electrons. They fired them at a barrier with two slits, just like that experiment that showed light acting like a wave.
Did the electrons form an interference pattern too?
They did. It was undeniable proof that matter could act like waves. De Broglie was right.
So this wave-particle duality, it wasn't just a quirk of light, it was a fundamental principle.
And that brings us to one of the most important equations in all of physics, the Schrödinger equation.
Schrödinger. That name rings a bell.
It should. This equation changed everything.
The Schrödinger equation. It's like the master key to quantum mechanics, right?
It's a game changer, that's for sure.
So how does it actually work? Our sources mentioned something called a wave function. What is that?
Okay, imagine you're trying to track a bee in a garden. It's buzzing around, going from flower to flower.
Right. It's not following a straight line or anything.
Exactly. So you can't really say the BIS here at any given moment.
It's more like it might be here or maybe there.
That's a great way to put it. And the wave function is kind of like a map of all the places that B might be.
Okay, so instead of a pinpoint location, it gives you a range of possibilities.
Exactly. It tells you the probability of finding the B, or in this case, a particle, at a particular spot.
So it's like saying there's a 60% chance the electron is here, a 20% chance it's there, and so on.
Precisely. It's all about probabilities.
That's a huge difference from the old way of thinking, where you'd expect to pinpoint an electron's exact position.
Right, and this is where things get really interesting.
Because obviously in the quantum world, things don't always behave like we expect them to.
That's putting it mildly. And that brings us to another big one, Heisenberg's uncertainty principle.
Ah, yes, Heisenberg. I remember this from my physics class, although I'm not sure I ever fully grasped it.
It's one of those things that sounds simple, but has profound implications.
So remind me, what is the uncertainty principle again?
Basically, it says that you can never know both the position and momentum of a particle with perfect accuracy.
It's like the more you zoom in on one, the fuzzier the other one gets.
Exactly. It's not a matter of our instruments not being good enough. It's a fundamental limit built into the universe.
So the very act of observing something at that level actually affects what you're trying to observe?
You could say that. And this uncertainty, it's not just about position and momentum. It applies to other pairs of properties as well.
Okay, so if we can never fully pin down the state of a quantum system, how do we make sense of any of it?
That's a great question, and it's where the Copenhagen interpretation comes in.
Right. Our sources mention that too. It's like the rule book for understanding quantum mechanics.
Well, it's more like a set of guidelines, really.
Okay, so what are the key takeaways from the Copenhagen interpretation?
Well, for one thing, it really embraces this idea of probability and uncertainty.
Okay, so it's saying this isn't just a limitation, it's a feature, not a bug.
Right. The Copenhagen interpretation says that these quantum systems, they exist in this blurry state of possibilities until you actually measure them.
So it's like they're in multiple states at the same time.
Exactly. That's called superposition.
Okay, I'm starting to see where this is going. Schrödinger's cat.
You got it. The Copenhagen interpretation would say that until you open that box, the cat is both alive and dead.
It's only when you observe it that the wave function collapses and you get a definite outcome?
Precisely.
Wow, that is both fascinating and a little bit terrifying, honestly.
It's definitely a lot to wrap your head around.
That's for sure. So we've covered a lot of ground today, from the very beginnings of quantum mechanics with Planck,
Through the bizarre world of wave functions and uncertainty.
and this Copenhagen interpretation, which is still blowing my mind, by the way.
It's a lot to take in.
It really is. But it's also incredibly exciting to think that something so strange and counterintuitive underpins our entire reality.
Absolutely. It makes you look at the world in a whole new light, or should I say wave.
Huh. Very good. It just goes to show that the universe is full of mysteries, and the more we learn, the more we realize how much we still don't know.
And that's what makes it all so fascinating. Right.
Exactly. Well, on that note, I think we'll wrap up our deep dive into quantum mechanics for today.
Until next time.
Thanks for listening.